All right, so let's start by going over this implicit solution problem for this differential equation. So what I told you to do, even if you didn't watch the video about how to solve such a thing, is to go ahead and try to separate variables and see what happens. Separate variables, integrate, see what happens. This is separable. You can get all the y's on the left and all the t's on the right. You could multiply both sides by y squared plus y, and you could, quote unquote, pretend like you're multiplying both sides by dt to write this differential equation as y squared plus y dy equals cos t dt. Okay, like usual with separation of variables, and then integrate both sides. And the integrals are easy to do, right? 1/3 y cubed plus 1/2 y squared plus c, but we'll just put the c on the right side like usual. Integrate cosine of t, you'll get sine of t. Yeah, let's put our plus c over there on the right. That you could call a general implicit solution. Why do we call it implicit? It's because we haven't explicitly solved for y. Do we want to try to explicitly solve for y? Probably not. Cubic equations, they're theoretically solvable for y as a function of t here, but it's not very pleasant. Excuse me. Maybe we'll see if Mathematica can do it, but it's not a pleasant thing. Can we make sure we satisfy this initial condition? Yeah. Replace t with 0 and y with 1. You get 1/3, so y of 0 needs to be 1. Replace again t with 0 and y with 1. 1/3 times 1 cubed plus 1/2 times 1 squared should equal sine of 0 plus c. But of course, sine of 0 is 0. This is c. And this is 1/3 plus 1/2. Get a common denominator of 6. That's 2 plus 3 over 6, or 5/6. Looks like c is 5/6, right? You get that? So the final answer, and this really is the final answer for an implicit solution, is just to write this equation again, replace c with 5/6. So we get 1/3 y cubed plus 1/2 y squared equals sine of t plus 5/6. That would be an implicit solution of this differential equation. We call it implicit because we haven't explicitly solved for y as a function of t. When you do solve for y as a function of t, that's called an explicit solution. Is it possible to graph? I wouldn't want to try it without technology. It would be a pain. Now, theoretically, you might say it's possible. I mean, you could start with this point as being on the graph. Oh, okay, that's 1 point. When t is 0, y is 1. How do you go beyond just plotting 1 point? One thing you could do is you could try to use Euler's method. You could try to use Euler's method. You also could, even without Euler's method, try to approximate the slope of the graph here at t equals 0 by plugging in t equals 0 up here and y equals 1. Because that point is the point 0, 1. If you plug in t equals 0, you get cosine of 0 is 1. Plug in y equals 1 on the bottom, you get y, 1 squared plus 1 is 2. 1/2 is the slope there. The solution through that point, the unique solution to that point, of the solution of the differential equation through that point, has a slope of 1/2 right at that point. So its linear approximation is aligned with the slope of 1/2. Of course, once you get further away, probably the solution is either concave up or concave down. And it's hard to say without doing more work to figure out what it is. I guess you'd have to maybe differentiate this equation again, find the second derivative of y with respect to t to see if you can figure out if it's concave up or concave down there. That is possible to do, though it is a little tricky because you don't know what y is. And so maybe I'll leave that to you to think about. Can technology graph it?
Yeah.
Yes, of course. Mathematica can graph it. And you'll do this on the assignment due Sunday with contour plot. Capital C, capital P. Possible this could be on the take-home portion of the exam, a Mathematica thing to do. Can do Wednesday next week. I'm trying to type in this equation here. Okay, go ahead and type it in. Y cubed over 3 plus y squared over 2. Contour plot is kind of like solve or desolve. You need double equal signs. Oh, whenever you're solving equations or whenever you're trying to plot an equation, use double equal signs because single equal signs in Mathematica will set something equal to something else, and you don't want that here. Sine of t plus 5/6. What kind of window should I use? Oh, I don't know. T goes from -5 to 5. Y goes from -5 to 5. Let's just see what we see. Hey, kind of pretty. There it is. That's the solution. Is it really? Well, it does go to the point 0, 1, it looks like. See it there? Right there is 0, 1. And look, the tangent line does look like it might have a slope of a half. However, there is a problem with this graph, even though it's pretty. It fails the vertical line test. There are vertical lines like right about here that go through the graph more than once. 3 times, yeah. That can't happen for functions, right? Functions have to pass the vertical line test. You've learned that since 10th grade or something. What's going on here? What's going on is there's these different pieces of the graph that pass the vertical line test are different functions that solve the differential equation. Like this piece right here, about like that, that passes the vertical line test. That would be a solution. But there's also a piece like right from here to here that passes the vertical line test, and that's a solution. Not a solution of the initial value problem that we had, but another solution of the differential equation. Can we make the slope field in here too? Sure. Vector plot will make a slope field, capital V, capital P. Put a 1 in the first spot, put the right-hand side function in the second spot. The right-hand side of the differential equation was cos t over y squared plus y. I won't worry about trying to make it pretty. We will see arrows in here. It's not a big deal. There we go. Yeah, it is following the slope field here. You see some arrows that look like it's following it here. You can make a slope field still. Although there does seem to be something contradictory in this. These arrows are practically horizontal and the curve is not horizontal at these points. What's going on there? I think the true horizontal slope field is touching this graph where it has a vertical tangent, and that's just an indication of weird things can happen when you're dealing with implicit solutions. I won't go into more detail. Okay. On the homework due Sunday, it also asks why is the solution guaranteed to exist by using something called the implicit function theorem, which is actually not a differential equations topic, though it is related to this differential equation. And essentially, it's because at the initial condition, you're not dividing by 0 on the right-hand side. Because you're not dividing by 0 on the right-hand side at that initial point. That's the essence of why the implicit function theorem says the unique solution of this will exist.